Hello. Yeah.
Okay. So next talk is by Dipan. He'll talk about distributedly computing cost of replacing connections.
Yeah. So welcome to my talk. So I will be talking about the paper which is like optimal distributed replacement paths. So this was a joint work with Wai-Jun Chang and Gopinath Misra and other students from NUS. So let's discuss what is replacement path first. So often graph theory is used to represent some places, and vertices are used to represent some places, and edges are used to represent to some connections between them. And weights of those edges are basically the cost of availing those connections. So one use of this is like you want to find the shortest path from a vertex to another vertex. So suppose you are running some service between a vertex S to T, and then the shortest path will be S to U and then U to T. Now, as we are representing real life networks, then maybe there is some, due to rain, there may be some water logging issues or pothole kind of thing. So you have to avoid some edge, and you may have to lose some S to U edge or U to T edge. And in that case, basically, your shortest path will get changed. So this new path is basically replacing the older shortest path. That's why it is called replacement. So yeah. So this path is denoted by this notation S to T avoiding the edge SU edge, and length of the path is basically S to T avoiding modulus value of. So in replacement path problem, you are interested in the distances S to T avoiding. You may be interested in the path also, but as of now, we are interested in distances. And so for all E belongs to S. And as I have mentioned that you are running a service between S to T, so the variant we will be discussing today is fixes some source and the target also. You have some fixed source. So suppose you are running a service between TIFR and IIT Bombay kind of. Yeah. So, yeah, and only one edge failure for each scenario here in this variant. So let's discuss what we mean by distributed graph algorithms. So in distributed graph algorithms, basically the computation is distributed over a network of computers or nodes. So nodes are arranged in some graph. So suppose there are computers in all the nodes, and they can compute something, some part of whatever the problem is, and you have to output something. So okay, so yeah, so the model we will be talking today about is message passing model. So you can send some message through these edges, and each node can communicate. So each node has some computational thing to do, and it has to communicate with each other. And a node can communicate with only its neighbors only. And so whatever the direction of the edges is, the communication is bidirectional. So even if the underlying edges are directed, so suppose the path is one way, but you can talk over that path to your adjacent vertex. So yeah.
Can you also communicate over edges that are?
Yeah. So you just you can communicate over the edges you are. So in this replacement path variant, we will be we will be just calculating what the cost of losing that edge will. So at the given graph is already. Like two graphs. Yeah, so you are just given one graph, and then so I will be discussing the problem statement in this time. So I guess. So suppose that is the edge, which is from vertex to that vertex. The graph is one. Graph has like the edge has some direction, but the communication, both the edges, the upper edge can say, upper vertex can send a message to the lower. So you can basically communicate with both. So basically communication thing is like bidirectional. Edge is one. This has nothing to do with direction and the weights of those edges. So there are other variants also. Today we will be talking about this. So the complexity here is computed in terms of round. So in a round, basically the node at first receive data from its neighbor. So suppose we are talking about the topmost vertex, then it receives the data from its some of its neighbors, and then it compute. And then it sends its some data. So in a round, all the three things, in one round, all the three things can happen. And so it may choose which information to which vertices are to be sent some information, and it may choose that all the adjacent vertices, the information need not be same. So it may choose this vertex I will send this data, this vertex I will send this data. And so depending on the size of message and number of messages allowed, there are two models in message passing model. That one is local model. Local model has like unrestricted message size and numbers. And one is CONGEST model. CONGEST model is basically you can send at most one message at a time by one particular edge. Different edges you can send different, and different vertices you can send. So in a round, maybe all vertices want to send some information, and that is fine, as long as with one edge there is one message on it. So one message, and size is at most log n bits in each edge. And so each vertex has, so we assume that each vertex has some unique log n bits and log n ID bits known to it, and they know the incident edges to them. So I will be talking about this a bit later also, what the initial knowledge is, but let's discuss one or two small distributed graph algorithms. So let's just take one short detour, and I will be back to the problem also. So yeah, so rooted distributed BFS tree. Suppose you have a root R and you want to do BFS of height h, such that every vertex u in that BFS knows the distance from R. So in distributed setting, what we can do is from R sends its all neighborhoods, all adjacent vertices that you guys are at level 1 or distance 1 from me. And then U1, U2, U3, those will be sending that you guys are at distance 2 from R, and so on. So if you are interested till height h from R, then it will take at most h rounds. So at most h round, you can do this single source BFS. Now, if it has multiple roots, like R1 to Rk, you want to do this BFS until height h. So R1 and R2, you send this data from R1 and R2 to the vertices which are at level 1, and then you want to do the same thing. But here, U1 wants to send both distance from R1 and distance from R2 to its children. So basically, U1 wants to send to U4 at that round. U1 will be wanting to send that the distance from R1 is 1. My distance from R1 is 1, so your 1 will be 2. And so U1 to U4, that edge will have 2 messages to send. And so that is fine, it's in local model, but as the name suggests, the CONGEST model will cause some congestion. So you want to send 2 messages, and that cannot be sent at one round. And so, so with random delay kind of thing, so it will just actually, with random delay, it will randomly wait for one message to be sent, and then after that, it will be sending the second message. So with random delay, it can be done in big O k plus h rounds. So k is the number of sources, and h is the height till which you want to do. But yeah, so we assume that if we have many messages like k many vertices, then that there will be a problem. So in CONGEST model, you can so message size is like big O log n kind of thing. Yeah, where n is the number of vertices in the graph. So if k is like log n or some huge amount, so then it will not remain log n, theta log n kind of. So yeah, maybe for 2 vertices it is fine, but if k is some square root and kind of thing, then yeah. So with random delay, you can do it in k plus h rounds. So let's discuss what we actually try to solve in distributed replacement path. So in distributed replacement path, you are given some s to t shortest path and a graph which is like directed graph. Today you will be talking about unweighted graphs only. So, and you have to output. So in sequential setting, you have to output actually the length of the path from S to T avoiding E for all edges in the shortest path. And so so suppose this U4, U5 is the U4, U5 is one edge. For that, you will need to output the whole length of the path. So, and in distributed setting, each UI should calculate the length of the path S to T, avoiding its adjacent edge. So basically U0 will be calculating this cost of losing this edge U0, U1, and then so on. So U1 will be saying that cost of, so after the calculation is over, U1 will be getting the cost of losing U1, U2 edge, and U9 will get cost of losing U9, U10, so on. So this is the problem statement for distributed replacement path. And so let's discuss about, initial information, I will be actually talking about it in a bit later, but yeah, so the source and the target vertex, the S vertex knows its, so I will be talking about it after one slide actually, so that will be clear. So yeah, so one previous work is like, there has been long line of research for centralized or sequential setting for replacement path. So in distributed, the only previous work was by Manoharan and Ramachandran in Sirocco 2024. So they discussed the results in like unweighted directed graphs and approximate. So this is approximate is basically 1 plus epsilon approximation for weighted directed graph. So so they gave an upper bound for like unweighted directed graphs of n to the power 2 by 3 plus square root and HSP plus D here. So we got tilde heights basically polylog factor after that, and HSP is the hop distance of from S to T, and D is basically undirected diameter of the graph. Yeah, because we are talking about unweighted here, the hop distance by the distance from S. So yeah, so they have also shown some lower bound of square root n plus D. And for approximate 1 plus epsilon approximation weighted version, they have given the same upper bound and lower bound. So in our paper, we have reduced the dependency on on HST. We given some upper bound of square root n to the power 2 by 3 plus D, and we matched it with so the approximation version of 1 plus epsilon approximation for weighted graph is we also give that same upper bound. And the lower bound, we actually matched it with the given upper bound. So that makes our algorithm optimal. And so this is but that lower bound works for unweighted directed graphs. For weighted directed graphs, 1 plus that box is still to be filled up. So yeah, let's discuss about the initial knowledge. But we are not actually sure. So 1 plus epsilon approximation, it will be in this. So the weighted case actually is exact. Yeah, it's not approximation. For unweighted, it's not approximation. For weighted, it is 1 plus epsilon. So that's. So let's discuss about the initial knowledge at least. So so for each E belongs to E in the path, both the endpoints knows that this edge is in the path itself, and the source and the target vertex knows that they are source and target, and also assume that each UI knows their distance from S and to T in the path. So we assume this, if this information is not known, we can basically calculate it in square root n plus T. I will not be discussing about that, how to calculate, but assume that each vertex UI knows that which part at which point it appears in the path. Okay. So yeah, so let's discuss about approach in our paper. So you are given the path and UI should calculate S to T avoiding UI. And so R is basically the replacement path. Let's assume R is the replacement path. So R can go away from, so R has to, so P is the shortest path. So R has to go away from P at some point before the edge fault, and then it has to march back. So after marching back, it can go through P itself. So it can go away from P and march back to P at most once. So this is known as detour of R. Now, if so, we will be dividing these cases depending on the number of vertices on the detour. So depending on how many vertices are on this detour, we will be discussing two cases. So short detour, if the detour has less than equal to n to the power 2 by 3 vertices, yeah, and long detour if it has more than n to the power 2 by 3 vertices. So yeah, length of that yellow path, that the number of vertices in that length. Yeah. So observe that this detour started at ui can be found by doing BFS at ui in G minus P. So if we start a BFS from U2 in G minus P, then this yellow path will be finding. So G minus P, we will be getting this path itself. So yeah, so because we will be needed for all the edges we will be needing. So we at once just remove that whole path and yeah, sorry, yeah, I should have mentioned that. Yeah, G minus P means removing the edges only. Yeah. So from U2, if you do BFS, you will be in G minus P, you will be getting this detour itself to U8. So we want to do BFS, we want to use this and we want to do BFS from each vertex in P of at most n to the power 2 by 3 hops because we are dealing with short detour as of now. So, but then we will have HST many sources and that will take in CONGEST model that will take HST plus n to the power 2 by 3 down. So that is not enough as of now. So, and we want to remove this dependency on HST. So, so one observation is like suppose we reach a vertex V from UI and UJ both at same round. So if we reach at same round, that means UI to V distance is basically from U1 and U2. If we reach to V at same round, that means U1 to V path. That's both the yellow paths are basically of same length also, because at each round we are going one. And after that, basically, after it merges to V, then the shortest path in that both will be same. Yeah. So now U2 to U8 part, this detour is avoiding the edges in this range, and that is avoided by the detour U1 also, detour starting from U1 also. So basically, this part is avoided by both the detours. So at that point, we will say that I will just propagate that BFS rooted at U1 only, because for U2 to U8, that detour, that is not, I mean, that is U1 to U8 detour is basically better for, I mean, that is avoiding more vertices. So at any time, at any point of time, we will have choice of like propagating only one BFS, and it will just propagate the highest, from which vertex it is like closest to S, and that will be sent by BFS. So at any round, there is no congestion now. And so this gives an algorithm for any UI to calculate the length of short detour in n to the power 2 by 3 rounds. And so, yeah, so the first and so one thing is that first and the last vertex in the detour can be at most n to the power 2 by 3 because all the detour is like n to the power 2 by 3 at most. So each vertex has n to the power 2 by 3 suggestion. So here I will be quickly going through this. So at so each vertex has n to the power 2 by 3 many suggestions. So at n to the power 2 by 3 round, UI will be sending the n to the power 2 by 3 data to UI minus 1. So we cannot just naively send all those data. So suppose here one observation is like U1 suggests some path. U1 may suggest some path like this path and this violet path from U1 to U7 to U3 to avoid the edge from U3 to U4. And then it will be sending by U2 and then it will have to send to U3. I mean, before sending to U3, it will go to U2. And U2 can see that data and it may update accordingly to send to. So U2 does not have to send both the data. So it can wait for the information from U1 and just update that information. So this is kind of pipelining. So this is like we use some kind of information pipelining for this. So information pipelining was previously also in some papers. So yeah, so this is one thing. And then for longitude, actually, I will just go with like apply in 1 minute because okay. So yeah, so we for length, longitude is like greater than equal to n to the power 2/3. Then we sample some vertices and name them landmark vertices. We say that among all the landmark vertices, at least one will be on that longitude, and accordingly we want to basically divide this whole detour in short fragments like n to the power 2/3 at most. So I will skipping this part, and so accordingly that longitude part you will need some S to L avoiding P, U, I, and so this we have done using some broadcasting and divide and conquer techniques, and so this can be done in n to the power 2/3 plus d rounds also. And so comparing so after comparing the short detour and long detour part, we can get with the best possible detour starting at UI. And so we use some similar strategies for weighted graphs, 1 plus epsilon multiplicative approximation. And we have also shown some matching lower bound using the framework given by Das Sharma et al. In Stock 2011. And so this is a gap. And so let's discuss about one further direction is like, so after the, so we focused only on one path, one source and target. So after that, another variant studied by Monoharan and Ramachandran is like they did distance sensitivity oracle. So they created some oracle which can answer for any source and target and one edge, what is the length of the path from S to T avoiding E. So this is compared in terms of how many rounds you take in pre-processing and answering rounds also. So they gave this upper bound. So if you multiply pre-processing with the answering time, both of them takes n to the power 3/2 actually. So that is like the upper bound, and then they have given the lower bound of like P is pre-processing and Q is query round. So P into Q is like we go till the end. So there is another gap between their lower bound and upper bound. So that's one direction. And yeah, so increasing the number of edges is also another direction. So thank you.
Are there any questions? I have one question. What are the bounds known if we are only considering S and T and no edges, nothing? We don't remove edges. What are the?
Then you have just shortest path, then square root n plus d is 7. Yeah.
Time for coffee.